Welcome to this presentation on pair sum in binary search trees (BST). Today we will explore a problem where we check for a pair of nodes whose sum equals a given target value in a BST. In this problem, we are given a binary search tree or BST and a target value. Our task is to determine if there exists a pair of nodes in the BST such that the sum of their values equals the target. Let's consider the first example. Here we have a BST with the values 7, 3, 8, 2, 4 and 9 and the target sum is 12. Upon checking, we find that the pair of nodes 8 and 4 adds up to 12, so the output is true. Now let's look at another example. In this case, the BST is 9, 5, 10, 2, 6 and 12 and the target sum is 23. However, in this tree, there's no pair of nodes whose values sum up to 23, so the output is false. To solve this, we will use a hash set. The approach involves performing an in-order traversal of the BST while keeping track of the visited node values. For each node, we check if the complement of its value, target minus node value, already exists in the set. If it does, we have found a pair. If not, we continue the traversal. Here's the code for the solution. The findPair function recursively traverses the BST, checking for pairs as it goes. It uses a hash set to store the node values in it has already visited. If it finds a complement in the set, it returns true. Otherwise, it continues checking the left and right subtrees. The key aspect of this code are if the node is null, we return false. The hash set is used to track the values of the nodes we have visited. If we find a value in a set that completes the sum, we return true. The time complexity is big of n because we visit each node once, and the space complexity is also big of n because of the hash set. Let's analyze the time and space complexity. Since we visit each node once in our traversal, the time complexity is big of n. The space complexity is big of n as well. Because the hash set stores up to n elements, where n is the number of nodes in the BST. In this problem, we have considered several edge cases. These include a single node BST, a tree where all elements are smaller than the target, cases with duplicate values, and large trees with up to 1 lakh nodes. To summarize, we use a hash set to track visited values. We implement a depth-first search to traverse the tree. The approach achieves big of n time complexity and big of n space complexity. This method provides an efficient way to find a pair of nodes in a BST that sums to a given target. Thank you for your attention. If you have any questions, feel free to ask. Welcome to the presentation on minimum operations to exit threshold value, the second problem. In this session, we will walk through the problem breakdown, approach, and the solution to determine the minimum number of operations needed for a given integer array. Our objective is to find the minimum number of operations required to make all elements in an array greater than or equal to a given integer k. The allowed operation is as follows. We select the two smallest integers from the array, remove them, and insert a new number calculated as min x, y times 2 plus max x, y back into the array. We repeat this operation until all elements are greater than or equal to k. Let's take a look at example 1. We have the array with elements 2, 11, 10, 1, 3 and k equals to 10. The goal is to make all elements greater than or equal to 10. In the first operation, we remove the two smallest numbers 1 and 2. The new number we insert is 1 into 2 plus 2, which equals 4. The array now becomes 4, 11, 10, 3. In the second operation, we remove the two smallest numbers 3 and 4. The new number we insert is 3 times 2 plus 4, which equals 10. The array now becomes 10, 11, 10. Now all elements are greater than or equal to 10. The answer is two operations. Now let's look at example 2, where the array is 1, 1, 2, 4, 9 and k equals to 20. In the first operation, we remove 1 and 1 and the new number we insert is 1 times 2 plus 1, which equals 3. The array becomes 2, 4, 9, 3. In the second operation, we remove 2 and 3 and the new number is 2 times 2 plus 3, which equals 7. The array becomes 7, 4, 9. In the third operation, we remove 4 and 7 and the new number is 4 times 2 plus 7, which equals 15. The array becomes 15, 9. In the fourth operation, we remove 9 and 15 and the new number is 9 times 2 plus 15, which equals 33. The array now becomes 33. Now all elements are greater than or equal to 20. The answer is 4 operations. To solve this problem, we use a min heap, also known as a priority queue. This data structure allows us to efficiently retrieve the smallest two elements from the array. We follow these steps. Push all elements from the array into the priority queue. Continuously extract the two smallest elements, apply the operation, and insert the result back into the queue. Keep track of the number of operations performed. Stop when the smallest element in the heap is greater than or equal to k. Now let's look at the code implementation. In part 1, we first define the function and initialize a priority queue. We insert all elements from the array into the queue. This allows us to retrieve the smallest elements efficiently. In part 2 of the code, we continuously perform the operation until the smallest element in the heap is greater than or equal to k. We extract the two smallest elements, apply the operation, and push the result back into the priority queue. Each time this operation is performed, we increment the operation count. Finally, we return the total number of operations. Now let's discuss the time complexity. The time complexity of this approach is big O of n log n. Pushing elements into the priority queue takes big O of log n time for each element. Each operation, which involves removing two elements and inserting one also takes big O of log n times. Hence, the overall time complexity is dominated by the priority queue operations. The space complexity of this solution is big O of n. This is because the primary space usage comes from storing the elements in the priority queue. In conclusion, using a priority queue allows us to efficiently manage and retrieve the smallest elements in the array. This approach guarantees the minimum number of operations needed to ensure all elements in the array are greater than or equal to the given threshold value k. That brings us to the end of the presentation. I now open the floor for any questions or discussion. Thank you for your attention.